Before moving on to look at our circuit symbol and our IV characteristics, I want to briefly mention our PNP transistor configuration. So as we've said before, it's the same basic idea and operation principles as our NPN transistors. We're just swapping roles of our electrons in our holes, and we're switching around polarities of some of our voltages. Again, we can talk about the forward active mode because that's where we're mostly going to be using these devices to amplify things. So in this case, we want our voltage between our emitter and base. So notice our notation changes a little bit here. Instead of V sub BE, we now talk about V sub EB. And instead of V sub BC, we now talk about V sub CB. So voltage at the collector with respect to the base. But the same basic idea applies in that we want to be forward biasing our base emitter junction while reverse biasing our base collector junction. So kind of combining a couple of the figures from previous videos on NPN transistors, we can look at what's going on with our PNP transistor. So we see over here on the left side, we have this VBB, which is applying a positive bias to the P side relative to the N side. And so what that's going to do is positively bias or forward bias this base emitter junction. On the right side, we have our collector, which is negatively biased relative to our base. So that's going to reverse bias our base collector junction as we want. So looking closer then at this VBB, we see we have this positive voltage applied to our emitter. So that's going to be repelling holes. So we're going to get hole injection into our base. We're going to have the same basic idea of a lot of holes here, 0 holes right here at this threshold of our depletion region. We have this concentration gradient, so we have holes moving towards the collector. Once they hit that depletion region field, they're going to be sort of swept into our collector region where they're going to be attracted by this negative potential here. So that's how our holes, sort of the main current flow is happening from those holes. We also have this electron current, we have some electrons being injected from the base. We see some of those are going to be recombining with these minority carrier holes in the base, so we have some recombination current. Again, we keep the base width small, we can get rid of most of that. We also have some electrons which are being swept across into our emitter. With appropriate doping of our emitter and base areas, we can sort of reduce that current as well. But overall, we see the same basic idea. We can also talk about our terminal currents. So now because we have holes instead of electrons here, that means our current is going to be in the same direction of that large arrow. So we have our emitter current is now going into the device, and our base and our collector currents are going to be leaving the device. So we have directions like this. So they've just swapped compared to our NPN device. However, beyond that, our relationship between our currents is the same as what we talked about in the previous video. So relationships between our terminal currents, so that's our IE, IB. See if I can write that a little bit cleaner so it's actually legible. So our IE, our IB, and our IC are unchanged from the NPN case. So that means for all modes we have that IE is equal to IC plus IB. And so of course we do that by treating this whole BJT as one node. We see IE is coming in, IB and IC are coming out. And then of course all the equations we talked about with our betas, our alphas relating to IC, IB, and IE also hold true. But of course keep in mind those are only relevant for forward active mode.